Hello, everyone, and welcome. We have a new week and, of course, a new great session as well. I hope you have already your spots ready and also your foods to enjoy this great session and to enjoy the food while you are learning more about, in this case, WebAssembly. We have a great speaker, Sohan, with us. Apologies, I'm really terrible pronouncing names. Shohan, I hope it's correct. I just bring you on board. Hello, Shohan. How are you doing?
Hey Hugo, I'm doing good. How are you?
All good as well. Thank you very much for your contribution and the availability to be here to share your knowledge and expertise with us. Without further ado, I'm going to just send over to you, but before that, just quick one. As always, as you know, if you have any questions, feel free to use the chat to share your questions, your comments, any feedback. We welcome you to just provide because it's really useful for us as well to learn how to improve things. Also, let us know where are you connecting from. We are always interested to learn more about you as well. We have many different people connecting worldwide with us, and I don't know if it's lunchtime, if it's dinner, or if it's uh, breakfast, but I hope you enjoy the food and enjoy this great session. Without further ado, Shohan, are you good to go?
Yeah, I'm good. Thanks,
Perfect.
Hugo, and thank you, Cloud Lunch and Learn. Quick introduction about myself. My name is Sohan Maheshwar. I'm based in Amsterdam, in the Netherlands. And yeah, I work as a lead dev advocate at a startup called Fermion. So we are in the WebAssembly space, and I think I'm fairly well positioned to talk about WebAssembly. A bit of background about me. I've always been in the emerging tech space, I think. I worked on chatbots and natural language processing from 2015 to about 2018 in a startup and then in the Alexa team. Of course, now we're seeing so much with LLMs and ChatGPT. I worked on serverless and cloud in AWS for a while as well. So I always sort of like to think about what's next in technology. And I think in the cloud space, the future of the cloud really is WebAssembly. So in today's session, we're basically going to do two big things. I'm going to do a deep dive on how WebAssembly works and why it is the way it is. And I'm also going to do a quick demo, and then I'll talk about how it will change cloud computing as we know it. Again, think of this as a live stream, so I'm looking at the comments. If you want to say hi or anything in the chat, if you have any questions, please put it up. I'd love to have a chat with you during the session as well. Okay, so I'm going to start off with a very bold claim, which is that the next wave of cloud compute will be powered by WebAssembly. I'm sure you're using cloud in your day-to-day basis, on whatever, AWS, Azure, GCP, something like that. And this could be via containers, serverless, good old EC2 virtual machines. But truly, we think that the next wave of cloud computing will be powered by WebAssembly, and we're going to talk about why today. And I'm a random person streaming on the internet telling you this, but if you don't believe me, maybe you will believe Solomon Hykes. So this is a famous tweet from 2019, so a good like 4 or 5 years ago. And most WebAssembly talks start off with this tweet, so I thought I'll stick to tradition. And he basically said, if Wasm and WASI existed in 2008, we wouldn't have needed to create Docker. And I'll explain to you what Wasm and WASI is shortly. So honestly, it is that big of a deal because the guy who made Docker is basically telling you this. So let's jump straight in. I'd be curious to know if anyone has actually used WebAssembly, and if you're not, well, that's completely okay because I'm going to tell you what it is, how to use it, how it works, and how this actually will change everything. So starting off with what is WebAssembly, and if I say the word WASM or WASM, it's essentially the same thing. It's just short for WebAssembly. The boring answer is it's just another bytecode format. So just another bytecode format. So a bunch of bytecode formats exist. This is one of them. Why is it special? Well, for many reasons, right? And I think one of them being that it is actually designed from the ground up to be a portable compilation target. What does this mean? So let's take a look by what we mean by this and another bytecode format. I'm guessing many of y'all are familiar with Java or how it works. So you write a Java program, and this compiles this to something called Java bytecode, which again is, bytecode. So you'll see, I think it's base 15. So you'll see like 0F and 61, 32. That's bytecode, right? And that bytecode is executed on something called a Java virtual machine, which can run anywhere. It can run on an ARM processor, on x86, on Linux, Windows, regardless, right? So any place that can run a JVM can run any Java code, and that was the idea. Conceptually, WebAssembly sort of works in a very similar format, where you can write code in any language, literally, right? So you can write code in C, C++, Rust, JavaScript, Python, Zig, Go, all of them. And this compiles to something called a WebAssembly bytecode, right? Or a Wasm bytecode, which is a Wasm module. Now, this is important. This WebAssembly bytecode essentially can be executed in any place that has a WebAssembly runtime. And WebAssembly runtimes are designed to be run anywhere. So Intel, ARM, x86, whatever, it would work. Windows, Linux, Mac, Raspberry Pi, it would work. AWS, Kubernetes, again, it would work, right? As long as it has a Wasm runtime to really run on. So that's essentially how it works. Now, when I say Wasm bytecode, essentially the thing here, what do I actually mean? Well, a Wasm module has two ways of being represented. Right? So this is a Wasm module. The one that you see the most, the one that you see out in the wild, or you will see later on today as well, is the actual binary format itself. As you can see, there's 00, 61, 73, whatever, that's number wang. If you get that reference, good for you. But this is the binary format. Now, this is typically more lightweight, and you will see this a lot as representations when you're building WebAssembly. But if you're into the, the compiler engineering, and if you're one of those people, there is also a text format where it is a little more human readable. I don't know about you, I can't read the binary format and tell you what the program's doing. But with the text format, I think we can take a fair guess as to what it's actually doing. So that's what a Wasm module looks like. The most basic Wasm module actually is just this, right? Literally just one line of code, open brackets, module, close brackets. I'm the sort of programmer who'll probably see errors even in this one line of code, but forgot the semicolon or whatever. But this is the most basic Wasm module. WebAssembly can also have functions, and they sort of look like this. And again, this is the text representation that I was talking about. I think it's fairly self-explanatory, but I'll take a look at it and let's go line by line. So if you take a look at line 2, it's a simple function to add two numbers. And you will see here, it says LHS, or left-hand side, which is an integer, 32-bit integer. And there's another parameter, which is the number on the right-hand side, which is another 32-bit integer. And the result is passed as another int 32. So you essentially get both the left-hand side number, the right-hand side number, and you add the two. We've also written another function called +1, which takes a single number right here. You can see x, and it adds 1 to that, and it gives you a result. Right? And in that function, you can call the first function, which is add. So, typical Wasm module with functions. So that is how it would be represented in text. Again, a few more things to know about WebAssembly. We saw how it could be a portable compilation target where you can write code in any language and it compiles it to this Wasm format that we just saw. Now, the history behind WebAssembly is that this was originally written for the browser, and hence the word web in its name. And a bunch of companies are using this, like Google and Figma, Adobe, Shopify, Roblox. They all actually use WebAssembly in their front ends because of its properties. It's lightweight, it's fast, it's polyglot, so different programming languages. And it was also designed, like you saw earlier, for you to just compile it once into a WebAssembly module and then run that on a number of targets. Now that could be, again, Windows, ARM, Intel, whatever. So how does that part actually work? Well, this is sort of what a WebAssembly module looks like, right? And there are a couple of terminologies that you have to be a little familiar with. So as you can see here, it says guest Wasm module. That's the Wasm module that we saw earlier with the function called add and with the function called +1, with one of them talking to each other. Like we said, for this WebAssembly module to work, it has to be in something called a runtime. And that in the WebAssembly module, in the WebAssembly world is called a host, right? These words are in a way interchangeable. It's not exactly the same, and we won't go into the details here. But think of it, if you can substitute the word host for a runtime. So that's what it does. If all of this is confusing to you, the analogy that I would like to draw is that of a hotel. Now, when you check into a hotel, you're a guest, so you have access to your room, and maybe you have access to a kitchen, a common area, maybe a swimming pool, but you don't have access to the other guest's room, or you don't have access to, say, the back office, for instance. And the hotel here is the host, right? So that's the sort of analogy where you can have multiple guest Wasm modules or guests in a host. In this case, the analogy being the hotel, right? With each of them have access to their particular thing and some common things, but not everything in the runtime. So that's the sort of analogy that I would really draw. And how does this work? Well, you write code in any language, and this compiles it to that Wasm module that we spoke about. And this Wasm module can run anywhere as long as there's a runtime for WebAssembly, right? And there are a bunch of runtimes out there. On the server side, we have things like Wasm time, that's pretty popular, and there's a Node.js experimental runtime as well. On the browser side, we have SpiderMonkey and Chromium, all of them supporting WebAssembly right now. So if you're watching this on, say, Chrome or Firefox, there's a good chance that the version you're using does support WebAssembly runtimes. Now, I just said something interesting, right? Which was, it was meant for the browser, but I mentioned something about server side as well, like what's going on there. So the thing is, up until 2019, WebAssembly was exclusively for the browser, right? And in 2019, the thing called WASI was introduced. And this is what was referenced in the tweet by Solomon Hykes. WASI essentially stands for WebAssembly Systems Interface, or a new kind of systems interface. All the things that make WebAssembly good for the browser actually can make it really great for server side. But for anything to run on a server, you need things like access to files, you need access to file systems, clocks, random number generators, sockets, and so on. So this needed an interface, which was WASI. So this thing called the Bytecode Alliance, think of it like either CNCF or W3C, but for WebAssembly. They essentially came up with the standards and protocols and frameworks called WASI, which enabled us to run WebAssembly on the server side. The great thing is it's completely independent of browsers, so it does not depend on any web API, no JavaScript, nothing. Right? You can actually run a WebAssembly module using WASI on the browser, and it extends Wasm's sandboxing to include things like input and output as well. A question that we get asked very often is, hey, you're saying all languages support WebAssembly. Is that really the case? And yes, in fact, if you look at the top 20 languages in Stack Overflow's report, you can see that all of them are supported by WebAssembly in various formats. This is something that's consistently evolving. So check out that webpage there. We always try and update it as much as possible. But if you have any questions, again, feel free to put it on chat. I'll try and get to as many as we can. I think Hugo's put up a comment saying we have Ireland and Netherlands connecting today, which is I think pretty cool, right? I think the internet allows us to connect on a very global basis. So yeah, please drop in some comments. I did mention that WebAssembly's strengths made it good for the browser, but it's made it great for serverless and cloud computing. And these strengths include the 4 points that you see here, and we're going to do a deep dive again into each of them. I already mentioned how it is cross-platform and cross-architecture, right? Any place that can run a WebAssembly runtime can run your code, and you're just writing it once. Something that is truly impressive and different about WebAssembly is that each WebAssembly module is sandboxed by default. Now compare this with a Java virtual machine or many other languages that you've probably written code in. all of those allowed access by default, and you had to deny access to other things by writing code. WebAssembly is literally the opposite, right? By default, no one can access a WebAssembly module that's within a host or a runtime. And even if you have to give access for a file, you have to give access for, say, a function or even an outbound HTTP call, you have to explicitly give it permission to do so. Now, this is very powerful in the world of computers and server-side and cloud because of how secure it can be, right? I can actually run untrusted code on, like, say, WebAssembly runtime because I know that it can't interfere with any other WebAssembly modules that I have running in the same runtime, right? So that is very, very powerful. There are a few things about its speed, its binary size, its startup, its execution that we will also talk about in a while about why it actually can be very powerful to run in the cloud. All right, so I hope I've piqued your interest a little bit. So many people are like, okay, you've spoken a lot. How do I get started with building Wasm, right? I'm sold. I want to write code. What can I do? I'm going to do a quick demo of writing a simple Hello World program using an open source tool called Spin. So Spin it's completely open source. It's the developer experience for building WebAssembly serverless or server-side apps. And essentially with 3 commands, you can actually create a WebAssembly app and have it running in the cloud. Spin is maintained by Fermion, the company that I work for, but it's completely open source. So feel free to jump into our GitHub. There is a bot for good first issues. So if you want to contribute to this open source project, feel free to do so. We also have a Discord channel. Hopefully we'll get to 5,000 GitHub stars very soon. We're at 4.5K right now, and it supports 15 plus languages. A quick shout out to what Spin actually does. Like we said, it's built with open standards like WASI that I mentioned earlier, and the WebAssembly component model and things that I'll talk about. You can do a few things with Spin. You can actually run large language models in a serverless fashion. You can have your own key value store. It's a CLI tool. You can also have an SQL database. And since this is serverless, you need events to trigger a particular function or an application. So right now we support HTTP and Redis triggers. There are also community written triggers for things like MQTT and I think a couple of others, SQS as well, maybe simple queue service. Again, feel free to write your own triggers and maybe contribute it back to open source too. So let's take a look at code. I know we are all technical people here, so we want to see code. This is just a small demo, a very simple Hello World on how you can build a WebAssembly app using this open source tool called Spin. So I'm opening up my CLI and I'm just going to check if you can see the screen. Yes. So all I have to do is, I did say 3 commands, so I'm going to do spin new. Now you can actually see the list of templates right here. Each template is in the form of a trigger and a language. The most popular trigger is HTTP. As you can see, there are a bunch here, but you can also see Redis right here at the bottom. And next to them, you can see the languages as well, right? You can see C, there's Grain, JS, PHP, Swift, TypeScript, Zig, etc. Let's do Rust today, maybe. Why not? Let me do Rust, right? And I'll just say cloud, lunch, and learn, right? CLNL. The description, well, self-explanatory. You can actually specify a path upon which this particular WebAssembly module is invoked. So you can say something like /verification, and only when you do xyz.com/verification will it route to your Spin application. Right now we leave it blank, which means any request to this URL will run your Spin application. I will do cd clnl, and I will open this folder in my what's this called? I forget. Oh, VS Code. There we go. There we go. It's going to make it full screen. And again, folks, feel free to put comments here. So there are 2 things you need to know about writing a Spin application or building a WebAssembly application using Spin. The first one is your entry point is a sort of TOML file called your application manifest. So this has some metadata about your application, stuff you don't need to know. And like I mentioned, it has a trigger. In this case, any route to your application, so just xyz.com, will trigger this application, but within the app, you can actually build routing, right? So you can have /verify, use a particular component here. I can add another component for like, say, /checkout. All of that will be in this particular file. And we are defining the things about the component itself. So when I compile my code, remember we said it compiles to a Wasm file, which is a bytecode format way of representing it. We can take a look at that file in a bit. And you don't need to know about this stuff for now. So let's take a look at the source code. This is simple Rust. Instead of saying hello, we'll just say hello lunch and learn, right? That's it. Ooh. I don't like typos, even in my demos. I did promise 3 commands. We have already done 1 command, which was spin new. So I'm going to say spin build, right? And what this is going to do is build this app locally. Now we're doing Rust, so it's going to use crates and build it locally. But the experience is exactly the same if you do this on Python or TypeScript or whatever, right? And so this is built right now, and I can actually just deploy this locally by doing spin up, right? And literally in less than a second, it created a local server. And yeah, I can just do a simple curl -i, right? And you can see there it says hello lunch and learn. Right? So in 3 commands, I had like a local testing and a dev experience around building a WebAssembly app. And I think that's pretty cool. And honestly, the fourth command, if I want to deploy this to the cloud, so actually deploy it, run it in the cloud as a live application, I can do that with just a simple spin deploy. This connects to the Fermion cloud itself. I've already created an account and logged in, of course. And it takes this WebAssembly module that you saw there and pushes it to the Fermion cloud, where this app is actually running live. So in about 10 seconds, yeah, you can see this here. Maybe I'll try opening this up on a browser. And in hardly few seconds, I have to just build this onto my screen on my Firefox. Yeah, there we go. In case you can't see this, I'm just going to. Yeah, so this app is literally running live right now. You can go to this URL and you will also see the same thing. I can just refresh this if you want. But yeah, that's how easy it was to get started with a WebAssembly app. And like I said, you can do it in pretty much any language that you want. So that was the demo, right, around it. Like I said, this is both a deep dive and talk about why this actually can be it will be the next wave of cloud computing. So there are 4 things that we think will, I have to bring, there we go. Can we see that? Yeah. That make WebAssembly great, right? Like the first one is binary size itself. Now, a typical Rust Hello World app compiled natively is about 2 MB. And if you do an ahead of time compilation where you're compiling it optimized for the target itself, you can bring that down to about 300 KB. A basic spin HTTP app is only 2.3 MB when you compile it just in time. And again, you can bring that down to about 1.1 MB ahead of time. Think of doing this in, say, a non-WebAssembly way using, I don't know, say, Node.js or something. And the size for a simple HTTP API on Node.js is significantly higher, right? So at scale, or if you want to save on cloud costs or be more sustainable, this starts making a big difference, especially at scale. And if you don't believe me, I'm just going to show you this as well. So these are all the files that we just built, right? So I'm just going to go to the target folder, and there is a folder called release. And if I do an ls-l, this Wasm file is that 2.3 MB file that I spoke about, right? And like I said, it's complete bytecode. So I have no idea how to read this basically. But the good thing is you don't have to worry about any of this, right? You're just writing code in the language you love, and something like a spin will convert that into WebAssembly, which then can be run anywhere, right? So really, you don't have to worry about any of that stuff. All right. Going back to, can you see my Oh, yeah, there we go. So the binary size is one of the things that is making WebAssembly pretty cool. The second is startup time. Now, WebAssembly was designed from the ground up to be very performant. And all of the decisions that the original creators took were keeping in mind things like performance. So for instance, it has a reduced instruction set compared to so many of the other bytecode formats and languages out there, which already make it smaller and more performant. The aim always was to get to as close to near native performance as possible. And we're actually seeing about, with Rust itself, it's only about 2.3x slower than native, which is very impressive if you start comparing, with other frameworks that exist out there. So the reason WebAssembly actually works in startup time, and this is the deep dive again, is how it is actually built. Right? So WebAssembly runs on something called a stack machine, and it is bytecode format for a stack-based virtual machine. We're going into the weeds of computer science here, but I hope you'll like this. Now, we earlier wrote a simple function to add two numbers, right? And this is what it looked like. Again, you have a parameter left-hand side, integer 32, same right-hand side, integer 32, and the result, integer 32 again. The program first gets the number on the left. So if you do add 4, 3, it gets 4, then it gets 3, and then it adds the 2. So in a stack-based machine, how this works is when you do line 2 local get LHS, that is loaded into a stack, right? It is loaded into a stack. Then you go to line 3 and you do get RHS, which in this case is 3. That number is loaded into the stack. Line 4 actually adds the two numbers up. Last I checked, 3 plus 4 is equal to 7. So what happens is the two numbers that are in the stack are popped outside of the stack. Right? And the result of the addition or of the operation is then pushed back into the stack. Now, how WebAssembly essentially follows this is it uses a just-in-time compiler, right? So the just-in-time compiler transpiles this into a different intermediate format that is then optimized further on based on the target. So you're essentially mapping this to a new representation, and then you're doing a JIT compile or a just-in-time compilation, which is why it is, or one of the reasons why it is actually so performant. So that is the reason why things like startup time actually can give you near native performance. We spoke a little bit about portability, where you can build this once, run anywhere, and we spoke about why that's the case as well. And we briefly touched upon security, right, which is the sandboxed execution model. Now, this is one of the key differentiators of WebAssembly, and let's do a deep dive on how this works. So going back to that old diagram, hotel, host, guest, etc., you have your Wasm module here. And we had written two functions to add and to increment a number, which called each other. And this is running on a host runtime. Remember, hotel, guest analogy. As a user or as a developer here, I cannot access any of this stuff by default, right? It's completely sandboxed. And you're like, wait, hold on. What can I actually do then? So what happens is Wasm actually lets you export functionality out. So in this case, this is the same program that we have written earlier, but all of these lines are the same, but we have added an export called Wasm add, which pushes that same program out. Right? So here's where things start getting interesting, because right now, the guest Wasm module has exported this one particular function that can now be accessed by a dev or by a user. Yeah. So the user can sort of talk to the runtime or the host, but not the guest Wasm module in it. Again, drawing, like, maybe stretching our analogy a little bit, a guest is coming to this hotel and they can maybe meet you in the lobby, but they can't come to your room, right? Again, very clunky analogy at this point, but just to do a callback there. Again, the user can invoke this function that is running in this host. At the same time, it also lets you import functionality. So as a user, I can import a functionality to print to the console. So here, I'm doing a console log, and I take in a 32-bit integer, and I can actually print that out. So as a user or as a dev, I'm supplying a function that can be imported into this guest Wasm module as well. Yeah, so that's the idea. How does that actually work? Well, the cool thing about WebAssembly is it has this thing called a shared linear memory. So what that means is, these are big words, so I'll break it down. So essentially, it's a contiguous block of memory that is shared between different Wasm modules within a host. In some places, in some compilers, interpreters, whatever, when you allocate memory, it randomly allocates different sections of memory within, your hard disk or whatever. Excuse me. But in the case of WebAssembly, it's a contiguous block of memory that is actually allocated to a module. And this is shared, it's called shared because the host runtime and the guest module have access to the same memory. And if there are other guest modules in that runtime, you'll have access to that same memory as well. If you take a look at the code now, in line 3, we're importing what is called a page of memory, right? And 1 in this case denotes 1 page of memory, which, if I'm not mistaken, is 64 kilobytes in the Wasm world. And in line 4, we basically say you init into the 0th position, 0th here, this particular string, which is hello world. And what's happening in line 5 is you're defining this function called hello world, which would init it in the 0th position and give it 14 kilobytes of memory, because there are 14 characters in hello world. So under the hood, this is the deep dive of how WebAssembly actually works. Because if you want to visualize this in a graphical way, we said that earlier, right? There's a guest Wasm module which imports a function to log something. It exports a function called hello world, and it's getting that data hello world. Now, all of this, the guest Wasm module and the user have access to the shared linear memory. So, you can read from the same shared linear memory. And the host only lets guest access certain memory and certain functionality because, like we said, it's sandboxed by default. So that was the longest deep dive on how WebAssembly works. I promised that I'm going to talk about the deep dive, but also how this would change cloud computing. Well, how will this change cloud computing? My answer is that it would change it gradually for now and then suddenly, right? Which means that WebAssembly is very much on the bleeding edge or in the early adopter phase right now. So if you're an early innovator, well, this is the time for you to check out WebAssembly. We're seeing so much interest from devs, startups, but also enterprises who sort of want to change and want to optimize their cloud builds, right? And they're looking at WebAssembly as a way to do this. If you take a look at the evolution of cloud computing, this is sort of what it looks like. In the pre-cloud era, and I'm old enough to actually remember it, you did all of it, right? There was like a server down the hall. I remember it always had like an air condition to keep it at a certain temperature, and there was cooling, and it was locked with like 5-6 padlocks. But you did all of it. You did your hardware maintenance and kernel drivers, you updated your OS, and put the app that you wanted online into that data center. And with the launch of things like EC2, right, AWS's EC2, we were able to virtualize those machines through hypervisor. So as a user, you didn't care too much about things like the physical maintenance, for sure, you didn't care about. You maybe at times had to look at some kernels and drivers. Once in a while, you had to update OSs and things like that, but it could run in the cloud. But of course, you had to take a look at your app. Things changed a little bit with containers, right? With Docker and then Kubernetes and etc., where a host sort of took care of a lot of these things, right? And you didn't worry too much about kernel and drivers and all of that. A large chunk of your development phase was writing the app and about making sure that it ran within the container, because then the containers could run everywhere. We're seeing this improvement with serverless, where as a dev, like you and me, we can only work on our business logic. And this is very powerful, and so many enterprises are using serverless. We really see WebAssembly as the next evolution of that. where you can only focus on your app and get truly serverless things, right? And I'm going to talk about that. Largely, we think that WebAssembly will change cloud computing in two big ways. One is, I think the need for clunky containers sort of disappear, because if you're using Kubernetes or if you're using containers, you will know that they are pretty expensive. You get like fairly large cloud bills with large deployments. And what happens is you tend to overconsume resources. What happens with things like containers is that you provision your sizes for your absolute peaks, and those can be high depending on usage. So for a large chunk of time, there is so much resources that go underutilized or underutilized because you've over provisioned for the peak of your usage, not for your average. There are enough studies, including on A16Z or Andreessen Horowitz, about how apparently 100 billion of market value is being lost because of these margins. There are a bunch of other, check out SysDig as well, about how Kubernetes, there's so much underutilization happening on Kubernetes, which increases your costs, increases your carbon footprint, and is generally not very efficient. The thing with WebAssembly is you can truly scale up and down, and you can scale it down to zero as well. And because of things like its fast startup times, you don't need to wait to scale for your peaks. You can actually scale to those peaks almost instantly, thereby reducing the need to sort of over provision. At the same time, a huge pain point that we see are app configs are pretty complex nowadays, right? Because there are just so many dependencies, there are just so many layers, and the bigger your company is or the bigger your product is, this just gets more and more and more complicated. And any modern app nowadays has a ton of frameworks and language dependencies and libraries that you ship alongside your code. So if you're writing a Docker container or anything, you're orchestrating this with Kubernetes, your release points have it for different OSs, different versions of language, like, Python 2, Python 3, or Go this and Go that. All of this, tends to increase your build sizes. And then imagine doing that across production, testing, beta, alpha, so on. This is not efficient. Again, it's costly. It increases your carbon footprint. It's not sustainable. So WebAssembly sort of solves all of that for you, because you can truly build once, write once, and run it anywhere. Remember that old tweet by Solomon Hykes? Most WebAssembly presentations don't show you the follow-up tweet to that, but I thought I will, where he says, so will Wasm replace Docker? And the answer is no. Imagine a future where Docker runs Linux, Windows, and Wasm containers side by side. I think the idea really is that WebAssembly allows you to run on things like Docker and Kubernetes and so on, but make it more dense, right? Make it more efficient, make it more portable, make it more serverless and things like that, where you can actually run thousands of spin apps, for instance, on like a Kubernetes cluster, and actually run it efficiently so that you're provisioning just the right amount of resources. Just to give you a lay of the land in terms of containers plus Wasm, think of containers and Wasm as fast friends. Excuse me. Docker Desktop supports Wasm runtime. Spin can be run on Kubernetes, including things like Azure AKS. I think there's some work on EKS, Amazon EKS, and also KWasm that's going along. We literally just wrote a blog post and launched an OpenShift integration. So anywhere where you have Kubernetes or OpenShift, you can also run Spin. And I'm going to show you a quick demo that I pre-recorded. So this uses a Spin K8s plugin that my colleague Chris wrote. And if you write a Spin app like the one I showed you, you can just scaffold that to a Docker namespace. Like in this file, it just created a Docker file, created a YAML, and then you can just push that to it pushes an image to a registry, and then you deploy it. It creates a deployment, service, and ingress that you can access. So then if you do the get SVC, you can see that there is something on your local host, and you can have that local host up and running with your Spin app, right? This is exactly the same Spin app that I showed you live right now. It was running in a Kubernetes cluster using something called a Spin K8s plugin. Also, very soon, in the next maybe month or so, we are going to have a big launch in the Spin and Kubernetes space. So, watch out for that. All right. Again, if there are any questions, please feel free. Please feel free to put it in the chat. I'd love to take any questions that you might have. I mentioned earlier about how the two big places WebAssembly can help cloud computing was fixing, large over-provisioned containers. The second one we think is to fix serverless itself. Just to context set, serverless is a coding pattern in which you and I as a dev, we don't write a server process like a daemon or a socket server. We only focus on our business logic, and the entry point is an event handler. Of course, with things like Azure Functions and Lambda, serverless is popular, but like with those products, serverless does have something called a cold start problem. So what this means is essentially like a Lambda function, for instance, runs on something called a KVM or a Linux virtual machine, and these are running in the cloud. So when an event hits that particular function, it takes about 200 to 250 milliseconds for that function to get warm and then start and then execute this particular program. And sometimes based on things, it can take even up to 2 to 3 seconds. And you as a user or a developer, you're actually paying for that entire time. So in a way, there is some compute resource that's being wasted because of this cold start problem. This is a well-known sort of thing in serverless, and there are so many ways people have tried hacking around it, including keeping a Lambda function warm with like periodic pings so that there is no cold start and you can start faster. With WebAssembly, right, because of all of the things that make it great that we just spoke about, cold starts become a thing of the past. You can actually execute a Spin app serverlessly in less than 2 milliseconds, right? Because of WebAssembly's small size, because of its startup time, and we spoke about why, we're able to cold start a module on every execution within a millisecond of Spin. So I think that's pretty cool. You can see the benchmark between a Lambda function and a Spin app as well. And we're able to shut it down to equally fast, right? We're able to actually scale it down to 0, again, because of how WebAssembly is built. So the technology itself is giving us this opportunity to do serverless, but do it better. And this can truly lead to a request-based serverless architecture that optimizes on resource utilization. Now, if you're a small company, you're looking to save as much costs and be as sustainable and carbon neutral as possible. So you're not over provisioning, but you're optimizing it to scale for 0. If you're a large company, these things make so much of a difference when you're doing this at the scale of millions, right? So you can actually deploy and run Spin serverless apps or WebAssembly serverless apps and then scale them back to 0. And this architecture actually results in getting compute performance that would even be too small to run in like an empty Kubernetes node, right? It is actually that lightweight, and we showed you why. And the cool thing is you can truly achieve serverless in the sense that you can run this regardless of your operating system or a lock-in into a particular platform or a cloud provider. So right now, if you're running serverless, you're either running it only in Lambda or only in Azure or whatever. But now with WebAssembly, it's agnostic of your provider itself. So you could theoretically have true serverless by having it run in different places, regardless of platform, OS, etc., because of the portability of WebAssembly. I'm very excited about some of this, but one of the things that excites me the most is this thing called the component model. Now, this has been in talks for a while, and it was launched in a big way late last year, and it's in preview too, so it's fairly stable right now. But essentially, the component model is a way of rethinking how we build apps in general, right? Because right now, if you're writing an app, you typically write it in the same language. But with the component model, thanks to WebAssembly's portability and polyglotness, you can write a program in different languages. So for instance, you've written an app in JavaScript, but you're like, hey, I need something that passes YAML, and I need something that formats my date. Maybe someone's written a YAML parser in Rust because Rust is very good. It's a low-level language, so it's good at doing things like parsing, and it's faster. And maybe someone's written a date formatter in Python because Python's good with numbers. You can actually import these two things into your JavaScript application. Yes, that's right. You're writing an app in JS, Rust, and Python. Literally in the demo that I showed you earlier, you can do the same as well. Maybe I can quickly show it to you. I'll do that. So this is what we wrote earlier. I can just, if I do an ls, you can see this is written in Rust, but I can add a component that's written in Python, right? So py component, a description, and path could be /py. Oh, I have to put a slash. Right? And if I open up my code, I can actually see in my spin.toml that I said earlier, there is a new component for /py. Right? And let me open my py component. I can say hello from the Python component. Ooh. Let's run this code now, and we'll actually see that there are two routes, right? So I do a spin build, and I do a spin up, and you can see that there are two particular routes with using two components, one written in Rust, one written in Python. So here I can just do a curl. I still get it from the Rust component, but I can do, I can do the same thing. Curl /py, right? And it says hello from the Python component, right? So I think that's pretty cool. Oh, I don't know if you saw this. Yeah, you saw this bit. So the component model really excites me because of the fact that we can sort of rethink how code is built, how serverless works. Essentially, like I said, you have a Wasm module written in any of these languages, and we know it's portable and isolated and fast and all of that. You can compose applications with different components, like Lego blocks. Actually, I'm not even making this up. So you have a component A here, which has a core Wasm module, which exports a certain functionality. We spoke about that earlier. And maybe component B wants to import a certain functionality, right? These two can be written in different languages like Rust and Go, and they can work with each other to form a new component called component C. And each Wasm module has its own memory, as you can see here. This memory, this component A has no access to component B's memory. Component B's memory has no access to component A's memory, right? Even though they're part of the own shared linear memory, they're different blocks, so there's no access, and it's sandboxed by default. So do check it out. It's a very interesting way of actually looking at composing applications. We're almost at the end of the presentation. Some use cases for WASI, Wasm, etc. Think of anything that needs quick startup times, where size of workload matters, where security matters, where portability matters, or any of these. And I would bet that a good chunk of cloud applications or cloud use cases actually fall under this. Right? And when you add the spin developer and operator experience, you actually get a very seamless way of building apps. In the cloud, we're looking at things like functions as a framework services and extensibility with the component model that I just showed you. People are writing their own plugins. Say, for instance, you have marketing automation software. Maybe you need a plugin to do something specific. You can bring your own code to a SaaS platform. It's super lightweight. Run that Wasm code to do something custom. Also makes a lot of sense in things like IoT and on-the-edge devices, because again, it's so lightweight and fast, it can actually sit on the edge, do something while consuming very few resources. So yeah, I mean, that's pretty much it from me. Feel free to connect with me on LinkedIn. Check out developer.fermion.com or go to our GitHub and check out Spin. We also have a Discord where you can hang about and chat with us. We'd love to hear from you. Yeah, hope you learned something new today. Happy to have more deeper discussions around Wasm sometime here. And yeah, thank you for your time.
Great session, Sohan. Thank you very much. It looks like we don't have to be honest, the crowd today is a bit shy, but we still have time. And if you have any last minute questions, feel free to just raise those questions in the chat. I actually have a few questions for you, just to give you some context. Of course, see, this group is heavily followed by an audience that are Microsoft enthusiasts.
Nice.
So, so as you know, of course, Microsoft has the offers the Blazor with
Yeah.
WebAssembly. What could be, I know I'm playing the devil's advocate here. So what could be the highlights that you would say that Spin could differentiate when comparing with Blazor? I know that one of them would be the language support, of course, because Blazor mainly supports C#. But do you have anything else that you would want to highlight?
Oh yeah, for sure. In fact, first thing, I think it's cool that people here are from Microsoft. So the core of our team are ex-Microsoft Azure people. So including the CEO, the CTO, our head of product, and a bunch of, and I think most of the founders were all in the Microsoft Azure team. They used to work for something called Days Labs, which made Helm, if you've used Kubernetes, which was then, I think, taken over by Microsoft. So yeah, Blazor is something that we have closely worked with and have checked out. Like you mentioned, Blazor I think is only for C#, but it sort of is powered by WebAssembly. In terms of, I think, startup sizes and performance, I don't think it gives you as good as a performance as something like a Spin or Wasm time as a runtime itself. Haven't done latest benchmarks, so it's right now confined to the C# space, right? It's pretty cool that most enterprises do use C# in some places, so it's a good entry point if you want to use WebAssembly from a C# point of view. But yeah, I think it's limited to that ecosystem, essentially.
Yeah. Okay, great answer. Thank you very much. Another one which is really common is, well, if I'm not wrong, at least based on my experience, WebAssembly typically is used heavily in scenarios of client-side applications because, as you explained, you have your app all packaged and running in the browser. But in certain scenarios when you have critical applications, so for example, if you have an online store that needs to process payments, of course you cannot, you need to integrate typically with a server-side system payment service. The main question is, how do you guys address security to ensure that, for example, your WebAssembly app is the entity or the authority that is allowed to perform the payments and no one else? And we know that, of course, when you have applications running in the browser, you can always inspect the traffic and see what secrets and everything that they are exchanging. So how would you address this in Spin?
Yeah, no, actually, that's a good question, and I think the component model does a lot in that regard, right? In fact, we have a sample out where it does authentication via GitHub using the component model, where there is a component that only does this. And say you've written an app, like whatever, like an online checkout, you can integrate that sort of component to do this authentication on your behalf. Now, the good thing about this component model is that, assume there was a malicious actor even in that module, it would only be able to give access to the things that you give access to. So in terms of like getting malicious access to other things in your memory, there's no way for it to access that because by default it is sandboxed. Right? If you look at things in the past like your Java virtual machine or other things, by default it was allow all, access all, and you had to write code to sort of like, say, hey, no access to anyone and things. But here by default, you can't make inbound, outbound calls, nothing. It's completely security sandboxed. So typically we say that the question is, how do you give access to people as opposed to, is it safe? Because by default itself, there's no way you can access it, any WebAssembly module. And in fact, maybe I can show you a quick slide. I'll have to open a different slide of how this would work in the component model itself, right? And I think it would make sense there. Here we go. Right? So say we have, can you see my screen, Hugo?
Yeah, all good.
Yes. Right. So say this is an auth middleware component, right? It does authorization for you. And the rest is stuff that we have written. Now, in this case, suppose something actually happens and there's a vulnerability in an upstream component, right? So there's no need to mitigate this by doing everything again, right? All you have to do is, just change the upstream component and things would work because the middleware still is going to work as is. In a different scenario, say there is a vulnerability in your business logic, right? Again, there's no need to rebuild all of the stuff that you see below. You just fix your business logic itself. Because as you can see here, the middleware component only talks to an incoming handler and that's it, right? And an environment. So even if this is something that's malicious, it's not going to affect anything in your eventual business logic itself.
Okay.
Yeah.
Last question, which is typically, as you know, one challenge we used to face when we were adopting monolithic a big time ago, a couple of years ago. But one of the main problems of monolithic, as you know, is anytime you need to change something, you need to pretty much deploy the big elephants. In this case here on the WebAssembly, if you have a really enterprise level application with many hundreds of components, which can be easily go in that direction, if you need to fix an issue in one of the components, you need to deploy everything again and probably test things and do some regression testing and so on. Is that correct?
Yeah, so I wouldn't say you have to deploy all the components. I think from a deployment point of view, it would follow like very similar microservices architectures that are used in like say a Lambda or an Azure, where you deploy that function and then you'd sort of do the end-to-end and the regression test to make sure that the entire system works, right? So it would follow like a very similar model as opposed to deploying like your entire enterprise application again.
Okay, but in that case, you are saying that we could split the app into different microservices using different components. And then how would you connect everything to run the WebAssembly app in the browser?
I mean, I guess so. This would again depend on what your program is, right? It could be you can compose it like in a component sort of way. Typically, with any spin app, you need a trigger to run the spin app. So it could be like HTTP, Redis, SQS, whatever, and so you have an event that's actually running that particular thing, right? So you can also make outbound calls to like other services and other APIs through your spin app as well. And if you're composing like an app, like say in a component model which is made up of different components, you can choose to just update that one component that you made changes to, then do the end-to-end test to make sure that the component is doing what it's supposed to. So you have like CI and things like that, and your application's up and running.
Okay, but in that case, you are talking about scenarios of having just let's say components or just small functions to do a single operation, right? So now let's imagine that we have a web app on top of that built with WebAssembly, and that web app, of course, is using those functions, those components to just do operations such as create a receipt, do a payment, and more. I assume those components there, they are not running in the browser, so they are just functions that are supported by the WebAssembly app. So that means what would be the advantage of using this approach about Spin and WebAssembly for those components, and not, for example, use the cloud native service such as Azure Functions or even the AWS Lambda functions, as you mentioned?
Yeah, I think two things, right? So one is in terms of like just speed and execution with serverless like Azure Functions and Lambda, there is a cold start problem, and especially when speed matters, you want to sort of try and eliminate those cold start problems and the costs that you incur for that. And with the technology of WebAssembly itself, you can overcome cold start problems and you can scale to zero. So when you're not using it, it's not like there is a warm function running. You've actually closed it, scaled to zero, and you have no footprint at all. And secondly, I think if you're running, say, on like a containers, right? And right now, maybe you can, I don't know, like I don't have exact numbers, but you can actually run far more denser Kubernetes clusters when they have spin apps in them, only because of its binary size and how light it is. And if there was a very interesting post on sysdig about how most of the containers right now in the cloud that people run are over provisioned because people provision for the peaks, right? The highest the usage is going to be. And it sounds counterintuitive, but idling resources actually take up a lot of computing power, and
Yeah.
it's supposed to be utilized. So the more you utilize a machine in the cloud, the more efficient it becomes.
Yeah.
Again, it sounds counterintuitive, but that's how it is, because if it's idle, it's still taking a lot of power and it's not doing anything. But if you're using it up to its full capacity, it's being more efficient because it's doing a lot more, right? And
Yeah.
I think by running spin apps, you can densely pack many spin apps in a multi-tenant way. So you're actually getting full value out of that system that's running.
Okay.
Yeah.
All right. Thank you very much. I don't know if anyone wants to share something before we drop. If not, I would say from our sides, thank you very much for being here. I appreciate your availability to be here and share with us. It was great to know about Spin. And if you have any links, that's probably the attendees can follow up on this. If you want to share in the chat, so I can share them, or even you can share directly in YouTube. We have a lot of people that's actually due to unavailability to be lives, they watch these sessions offline, so they will be able to access the links as well, the resource, if you want to share.
Sure. Yeah. Just go to github.com/fermion/spin or developer.fermion.com. Yeah, just try it out. I think that's the best way to check out the power of WebAssembly. Tell us what your feedback is. If you have any improvements, ideas, we'd love to hear from you. And yeah, you too, Hugo. We'd love for you to try it out.
Perfect. Thank you very much. I promise when I have some time, I'll give it a try. All right. Without further ado, I just want to say thank you, Sean. It was a pleasure to have you here. Thank you everyone for watching this session. Next week we will have more sessions coming up as always. And in the meantime, stay well and enjoy the rest of the week. Okay. Thank you very much. Have a great day.
Bye.